Hello again, and thanks for coming back here for our IGCSE Math series. According to the IGCSE Mathematics curriculum, 0580. This is the first section of Chapter 8, which deals with probability. We will introduce the concept of probability and cover topics 8.1 and 8.2 of the probability chapter in that video. Let us begin by answering the question, what is probability? Probability is defined as the study of chance or the likelihood of an event occurring. For example, we might say it is impossible for a unicorn to appear out of nowhere in a public park, but it is certain that the sun will rise tomorrow morning. In fact, we frequently use words like impossible, unlikely, even chance, likely, or certain to describe the likelihood of an event in our daily lives. However, in mathematics, we use a probability scale of 0 to 1, with 0 indicating an impossible event and 1 indicating a certain event. Actually, the probability scale is a term we frequently use when studying probability because it allows us to quantify the likelihood of various events occurring. Actually, probability does not tell us exactly what will happen. In fact, probability is just a guide, and cannot guarantee a specific outcome. For instance, if we toss a coin 100 times, we might expect it to land on heads half the time because there is an even chance of it landing on head or tail. However, if we record the outcome of that experiment, we may get 48 heads, 55 heads, or anything else, but in most cases, it will be a number close to 50. Okay, before we continue with our probability study, let us define some other important key terms and terminology we often use in probability. An experiment is a repeatable activity with observable or recordable results. For example, flipping a coin, rolling a die, conducting a survey, weighing an object, and so on. Because each of those activities is repeatable and produces a result, you can record it. For example, you can roll a die as many times as you want while recording the outcome. Trials are the repetitions of an experiment. For example, each time you toss a coin is considered a trial. An outcome is the potential result of a trial. When we roll a die, the possible outcomes could be any number from 1 to 6. A sample space is the set of all possible outcomes of an experiment. For example, if we flip a coin, the sample space is the set of all possible outcomes, heads or tails, and if we roll a die, the sample space is the set of numbers 1, 2, 3, 4, 5, and 6. An event in probability is a collection of possible outcomes that can be defined as a subset of the sample space of an experiment. For instance, let's consider the set of all possible outcomes of a standard experiment with a 6-sided die. We can define event A as getting an even number on the die. Therefore, event A will be the set of numbers 2, 4, and 6. In general, we use capital letters like A, B, or C to denote events. To quantify the size of an event, we use the notation N of A, which denotes the total number of possible outcomes for event A. In the case of this event A, N of A will be equal to 3 because there are 3 possible outcomes that satisfy the condition of getting an even number. However, we must be aware of the word possible in the definition of N of A. For instance, consider event B in our standard experiment with a 6-sided die, or event B includes all outcomes that are greater than 4 but less than 9. So, by definition, event B will be then the set of 4 outcomes, 5, 6, 7, and 8. Nevertheless, we cannot say that N of B equals 4 because we must only consider items that are possible outcomes of the experiment. In this case, outcomes 7 and 8 are not possible because they are not included in the sample space of the experiment, which consists of the numbers 1 to 6. Therefore, we must exclude them from the count, and n of b will be equal to 2, representing the number of possible outcomes that satisfy the condition of event b. The probability of event b occurring is denoted by p of b. And we usually pronounce it as the probability of event b, which can be calculated by dividing the number of outcomes in event b, n of b, by the total number of possible outcomes in the sample space, n of s. By plugging the number into that equation, we get the probability of event b equal to 1/3. In fact, probabilities can be expressed in a variety of ways, including fractions, decimals, and percentages. For example, this probability of 1/3 can also be expressed as 0.33 or 33%. Before we go any further, I'd like to point out that this equation for calculating the probability of an event by dividing the number of outcomes in the event by the total number of outcomes in the sample space is only true if each outcome in the sample space is equally likely, which means that each outcome has the same chance of occurring, as in our example of a fair six-sided dice. For example, if we are using that spinner in an experiment and the experiment's outcome is where the arrow will land after spinning, that experiment will have 4 possible outcomes, each with an equal chance of happening: red, green, yellow, and blue. Then the probability of the arrow landing on red, for example, is 1/4. But if we use that other spinner in the same experiment, which also has the same number of possible outcomes, the possibilities of the arrow landing on red are much higher. In fact, the area suggests that the probability is 5/8. So, please be careful when applying that rule, as it only works when every outcome has an equal chance of happening. As we have learned, the sample space is the set of all possible outcomes of a random experiment, while an event is a subset of the sample space set. To help us visualize probability problems, we can use a Venn diagram, which we are already familiar with from our study of sets. By using a Venn diagram, we can gain a better understanding of the various types of events and their relationships. To start, let's consider a simple example.
In a class of 50 students, 30 study physics, 23 study biology, and 12 study both. What are the chances that a student chosen at random? 1. Takes only physics. 2. Takes only biology. 3. Does not take either biology or physics.
To solve this problem using a Venn diagram, we can start by drawing a rectangle to represent the sample space of 50 students. This rectangle represents the universal set of our random experiment outcomes, which is whether or not a student studies a particular subject. We can use the Greek letter psi inside, or outside the rectangle, or simply use the capital letter U, or the capital letter S to represent the sample space. Next, we'll draw 2 circles to represent the students who take physics, which we'll call event P, and the students who take biology, which we'll call event B. Since some students study both subjects, the 2 circles must overlap. Using the Venn diagram, we can visualize the relationships between the different events and the sample space. We can then use the diagram and the given information to determine the number of outcomes in each section of the sample space. The area where the circles overlap represents the 12 students who take both physics and biology. Therefore, the area of the circle that represents the set of students who take physics only will be 30 minus 12, which equal to 18 students, and the area of the circle that represents the set of students who take biology only will be 23 minus 12, which equal to 11 students. The area outside of the circles represents the students who do not take either subject, which is equal to 50 minus 11 minus 12 minus 18, which equal to 9 students. To find the probability that a student chosen at random takes only physics, we divide the number of students who study physics only by the total number of students, which is equal to 18 divided by 50, or 36%. To find the probability that a student chosen at random takes only biology, we divide the number of students who study biology only by the total number of students, which is equal to 11 divided by 50, or 22%. Finally, to find the probability that a student chosen at random does not take biology or physics, we divide the number of students who do not take biology or physics by the total number of students, which is equal to 9 divided by 50 or 18%. Great! Now that we know how to use Venn diagrams to visualize probability problems with multiple events from the same sample space, provided that each outcome has an equal chance of occurring, let's take a look at another method for visualizing and organizing all of the possible outcomes of two events, which makes pattern recognition and probability calculations easier. When working with a random experiment, each outcome has an equal chance of occurring. To determine the probability of an event A, resulting from the experiment, we begin by identifying all possible outcomes in the sample space of the experiment N of S. Next, we identify all possible outcomes of event A, N of A, and then calculate the probability of event A by dividing N of A by the total number of outcomes in the sample space N of S. There are actually many ways to find out all the possible results of an experiment or an event. These methods include the systematic listing, the basic counting principle, and possibility diagrams. Let us start with the systematic listing method. The systematic listing method involves creating an organized list of all possible outcomes to ensure that none are missed. To do so, it's important to look for patterns to help identify all outcomes. For example, suppose we want to determine how many different four-digit numbers can be formed using the digits 4, 6, 7, and 9. We can use a systematic approach to organize a list of all possible outcomes. Let us start by fixing the first digit to be 4, and then systematically list all possible combinations of the remaining digits. For example, if we fix the second digit to be 6, we can get 4679 and 4697. Then fix the second digit to be 7, we can get 4769 and 4796. After that, fix the second digit to be 9, we get 4967 and 4976. By changing the first digit and continuing this systematic approach, we can generate a list of all possible four-digit numbers using the given digits, which contains 24 possible outcomes, giving N of S equals 24. Then we can answer any possibility problem that arises as a result of that experiment, such as what is the probability of obtaining an odd number from the combination of those four digits? Counting the number of outcomes of obtaining an odd number from the combination of those four digits from the list yields N of odd, which is equal to 12. The probability of the event odd is then equal to N of odd divided by N of S. With the number entered, we get 12 divided by 24, which equals 0.5 or 50%. Actually, when dealing with experiments with a large number of possible outcomes or complex sample spaces, the systematic listing method can be slow and inefficient. In such cases, we must utilize different methods. Let's begin with the basic counting principle. The basic counting principle, which we also call it the product rule, is a method or a rule that helps us find the total number of outcomes when two or more events or experiments happen together or one after another. The basic counting principle says that if there are p ways to do one thing, and q ways to do another thing, then there are p times q ways to do both things. For example, if you have 3 shirts and 4 pants, then you have 3 times 4 is equal to 12 different outfits you can wear. However, keep in mind that this rule only applies when all options are independent of one another. For example, choosing a shirt from the available options has no effect on the number of available pants options. So, if one option has an effect on the number of other options, then a straightforward multiplication is not the correct operation. However, as we will see in the following examples, that we can still use the basic counting principle to simplify the calculation. Suppose you want to buy a new car, and you have 3 body styles to choose from: a sedan, a hatchback, or an SUV. You can also choose between 4 different colors for the car: red, blue, black, or white. Additionally, you have 2 model options: basic or deluxe. The choices in that problem are independent of one another. For example, selecting a car body has no effect on the number of available car colors or car models, and vice versa. Then you can use the multiplication rule to find out how many different cars options you can buy. You have 3 options for the car body, 4 options for the car color, and 2 options for the model. So, you have 3 times 4 times 2 is equal to 24 different cars to choose from. But what if these choices are not independent of each other? For example, what if only sedans come in black color? Then you cannot choose any other car body with black color. This means that choosing the car body affects how many options you have for the car color. Because the car body choice will affect the subsequent selection, we will divide the car body selection into different options based on their effect on the subsequent selection. So for that specific case, the car body options will be divided into 2 categories: sedans and hatchbacks or SUVs. Now you have 2 paths, each with independent selection. In the first path, you have 1 option for the car body, which is a sedan. Then you have 4 color options: red, blue, black, or white, and you have 2 model options: basic or deluxe. So, you have a total of 1 times 4 times 2 is equal to 8 sedans to choose from. In the second path, you have 2 options for the car body, which are hatchbacks or SUVs. Then you have only 3 ways to choose the color: red, blue, or white, and still 2 ways to choose the model: basic or deluxe. So, you have 2 times 3 times 2 is equal to 12 different non-sedans that come in red, blue, or white colors to choose from. Now you can add up the results of these 2 paths to get the total number of different cars that you can choose from. We get 8 plus 12 is equal to 20 different cars that we can choose from when only sedans come in black. Let's go over this problem again, this time using the basic counting principle. To solve this problem using the counting principle, we must consider how many options there are for each number place in the 4-digit number. If we begin with the ones place, we have 4 options because we can use any of the 4 available digits. We only have 3 options for the tens place because we used one of the digits in the ones place. Similarly, we only have 2 options for the hundreds place, and only 1 option for the thousands place. It is important to note that the number of options for each number place is independent of the choices made for the other number place. So, by applying the basic counting principle, we get the total number of 4-digit numbers that can be formed using the digits 4, 6, 7, and 9, will be 4 by 3 by 2 by 1, which equals 24. As a result, the number n of s equals 24. To determine how many odd 4-digit numbers we can get, we know that an odd number always ends in an odd digit, so in our case, the 1 place will have only 2 options, which are 7 or 9. Then we have 3 options for the tens place, because we used one of the digits in the ones place. Similarly, we only have 2 options for the hundreds place, and only 1 option for the thousands place. So, by applying the basic counting principle, we get the total number of odd 4-digit numbers that can be formed using the digits 4, 6, 7, and 9, will be 2 by 3 by 2 by 1, which equals 12. As a result, the number n of odd equals 12. The probability of getting an odd number is then equal to n of odd, divided by n of s, which equals 12 divided by 24, which equals 0.5 or 50%. When using the systematic listing method to list all the possible outcomes of two independent events in a complex sample space, the probability of missing a possible outcome rises, as does the probability calculation error. In this case, the possibility diagram is an extremely useful tool for visualizing and organizing all possible outcomes, making pattern recognition and probability calculations easier. The possibility diagram is represented as a grid or table, with the top row representing all possible outcomes of the first event and the left column representing all possible outcomes of the second event. And each grid cell represents a unique combination of both events' outcomes. Let's consider the following example to demonstrate how to use the possibility diagram to calculate the probability of an event.
In a game where points are determined by a fair six-sided die roll and a coin toss, the points will be equal to the die value plus 1 if the coin lands on its head, and the points will be equal to the die value multiplied by 2 if the coin lands on its tail. What is the probability of getting a score higher than 5?
To begin solving this problem, we will first create a possibility diagram. The top row will display all possible outcomes from 1 to 6 for a six-sided die. Then there is the left column, which shows the coin flip outcomes, head or tail. Then, based on the information provided, we begin to fill each cell with the corresponding value. As a result, if the coin lands on its head, the cell value is equal to the die value plus 1. When the coin lands on its tail, the cell value is equal to the die value multiplied by 2. Let us assign the letter A to getting a score higher than 5. We can see from the table that there are 12 possible outcomes, which gives us n of s, which equals 12. Following that, we determine which outcomes result in a score greater than 5, which are as follows: 6, 8, 10, 12, 7, and 6. As a result, there are 6 outcomes that result in a score greater than 5. This results in n of A, which equals 6. Since the probability of event A is equal to the number of outcomes that result in event A, n of A, divided by the total number of possible outcomes, n of S, we get the possibility of event A, P of A, will be 6 divided by 12, which equal to 0.5 or 50%. In the following video, we will continue with Chapter 8, in which we will discuss different types of probability events and probability calculation methods and cover topics 8.3 through 8.6 of that chapter. Stay tuned for that. See you soon.